So welcome, I'm Peter Vickesland, and today we're going to be talking about some of the environmentally important reactions that can occur in natural waters. Thanks for coming. So to get started, we'll start with a generic general reaction. In this reaction, we're going to have A and B serving as our reactants. So they're on the left-hand side, and they're going to be in equilibrium, and we'll use a double arrow to denote equilibrium with two products, C and D. So on the left-hand side, we have our reactants, and on the right-hand side, we have our products. Now, these uppercase letters refer to the actual reactants and the products. And then in front of each of those, we're going to have a lowercase letter, lowercase a, lowercase b, lowercase c, lowercase d, and let me fix that lowercase b. And those are going to be referred to as stoichiometric coefficients, and those tell us the number of molecules or reactants and products that are involved in a particular reaction. So now we're going to take that general reaction, which I've just rewritten here to try and simplify things. We're going to use it to develop what's known as the equilibrium constant. Now, by definition, at equilibrium, the product of the concentrations of the reaction products, each of which is raised by its power of its stoichiometric coefficient, is going to be divided by the product of the concentration of the reactants. And again, that's raised by the power of their stoichiometric coefficients. So what does all of that mean actually in written form? Is we're going to take this general reaction, we're going to define our equilibrium constant K, and that's going to be equal to the concentrations of our products, so capital C, raised to its stoichiometric coefficient, lowercase c, product D raised to its stoichiometric coefficient, lowercase d, divided by the products. So this is not by the products, by the reactants. So this is A to the lowercase a, B to the lowercase b. And by definition, that's going to be the equilibrium constant. And this is going to be a constant for fixed temperatures and pressures. Now, in the expression as I've written it here, I've used square brackets. So, square brackets are telling us that we have concentrations in molar units. Now, when we write equilibrium constants, strictly speaking, we should actually be using braces. So braces, which are going to be like this, refer to activities. But for under many conditions that we're going to see, we're going to make the approximation that A is the same thing as the activity of A. So the concentration is equal to the activity. But in some cases, that's not going to be true, and we'll see that as we go through our lessons. So in this introductory lecture today, we're going to examine four general types of inorganic reactions. The first are acid-base reactions that involve the release and acceptance of protons. The second is going to be solubility or dissolution reactions that involve an equilibrium between a solid phase and the solution. The third will be complexation reactions that involve formation of a complex between a central metal ion and ligands that covalently bond to it. And then the fourth are going to be oxidation reduction, or redox reactions, that involve the transfer of electrons. So we're going to go through each of these four types of reactions individually now. In acid-base reactions, an acid releases protons, and a base is going to accept them. And this is a common definition of acid, and this was actually developed back in the late 1800s, early 1900s by Johannes Bronsted. And essentially, it states that an acid releases protons, or H+, and the base is going to be accepting those protons. We'll see some different definitions for how to define an acid later on. So one everyday example of an acid-base system that many of us are familiar with are ammonia-based cleaners. In ammonia solutions, ammonia is going to be present as the ammonium ion, NH4+. And using the Bronsted concept, we can characterize ammonium as an acid that's going to react with water, which is our base. And we see that the acid loses its proton, so we go from NH4+ to NH3, so that's the loss of a proton. And then the base actually gains a proton, so it goes from H2O to the hydronium ion, or H3O+. So to go further with acid-base chemistry, we'll first look at a couple of generic forms of acid-base reactions, and then we'll look at some specific examples for each of those. So the first generic form is going to be where we take our acid HB and we're going to react it with water to produce hydronium ion and our conjugate base B-. So an example of this was just actually on the last slide, but a separate example would be the conversion of, or the reaction, I should say, of hydrochloric acid, so HCl, plus water, to produce our hydronium ion, H3O+, plus chloride ion. So that's one example. Our second example reaction, in the exact same form as we have over here, where we have B- plus water goes to HB plus OH+, we can take bicarbonate ion, HCO3- plus water, and we're going to find and produce carbonic acid, H2CO3 plus OH-. So those are two generic forms of acid-base reactions, and then the actual specific reaction. So what we're going to do now is we're going to take those example reactions and we're going to convert them, and we're going to figure out what the form of the equilibrium constant is for that particular reaction. So our equilibrium constant for this first example reaction is going to be K, so for our equilibrium constant. And in this case, I'm going to write these in terms of the activity. So we'll use the braces. So this is H3O plus times the activity of the chloride ion concentration. And then we're going to divide by the activity of HCl times the activity of H2O. Alright, so that's our equilibrium constant for our first reaction. We can write an equilibrium constant for the second one. And in this case, again, we're going to have the activity of our two products, H2CO3, multiplied by the activity of OH-, divided by the activity of our reactants, HCO3- and H2O. Now, we can actually simplify both of those equilibrium expressions. And we can do that by noting that the activity of water is, by definition, because it's a pure phase, going to be equal to 1. So that means that K, in this case, is going to be the activity of our hydronium ion, H3O+, times the activity of chloride ion, divided by the activity of HCl. And then in this bottom case, K is going to be equal to H2CO3 times OH minus divided by the activity of the bicarbonate ion, HCO3 minus. So either of those forms for this last example reaction is appropriate, or either of the forms for the first involving HCl is appropriate. So our last acid-base reaction is actually just going to involve water. And essentially we're going to derive equilibrium constants for these two reactions. So in this case, K is going to be equal to the activity of the hydronium ion concentration times the activity of OH minus. And then that's going to be divided by the activity of water squared, since that's our stoichiometric coefficient. But if we recall, we said that the activity of water is going to be 1 by definition. So this ends up being simplified to H3O plus times OH minus is equal to K. Now, if we look at our second reaction on here, it's essentially the exact same thing as the first one, except we've eliminated one of the waters from both sides of the reaction. So we can write, in this case, K is equal to H plus times the activity of OH minus. And I want to point out that each of these lower two equations that's written on here is going to be exactly equivalent to one another. So these are equal to one another. And it's most explicit to write the first of these two, but oftentimes we just simplify things and just say that we have free protons floating around in solution. Now I've also just put two W's for each of those two expressions to indicate that we're talking about the ion product for water. So one last thing before we leave this slide, just to remind everyone that when we talk about pH, which is one of the two dominant variables in terms of describing water quality, is that when you remember that that's going to be the minus log base 10 of the hydrogen ion activity. And under many conditions, this is going to be approximately equivalent to the minus log base 10 of the actual hydrogen ion concentration. So, under some circumstances, we're going to have a solid that dissolves in water, and there's going to be an equilibrium between the solid phase and the ions that are present in water. An example of this is going to be the dissolution of calcium carbonate-based minerals, as is shown here. In this case, in this picture, we have limestone that's been weathered over time when it's been exposed to water to produce interesting geologic features here in France. So, before we move on, one of the things I just want to highlight in this slide is that I've used this lowercase superscript s to indicate a solid phase. And I've also used a lowercase superscript aq to designate something that's dissolved in water. So this is dissolved in water. Now, we'll be very explicit in always defining and using the subscript s to indicate solids, but a lot of times we're going to leave the subscript aq off just for simplicity's sake. So I'm going to write a few equilibrium expressions based on the generic forms of some solubility expressions, similar to what we've done in the past. And in this case, I'm going to simplify everything from the very get-go by noting that the activity of the solid phase is always going to be by definition equal to 1. So that simplifies what we're trying to write. So we can write our first solubility product, and in this case, since we're talking about solubility, This is going to be Ks, and it's going to be equal to the activities of our products. So M plus times the activity of A minus. And I don't need to include either water or the solid in this because their activities by definition are going to be equal to 1. So that's our first equilibrium expression. We can then draw the second equilibrium expression. And in this case, again, it's going to be Ks. And here we've got M plus as one of our products. And we have HA. So again, that's just the activity of our species HA. And to differentiate these two solubility constants, we're going to put a 0 next to this one, and we're going to put a 1 next to this one. And those are essentially referring to the number of protons that are reacting with a solid for a given reaction. So in the first case, there's no protons. In the second case, there's 1. And then our last type of reaction that we have on here is a generic form, where we've got metal ions that are reacting with water, and then we're ultimately producing some solid precipitates. And in this case, we're just going to call this Kn is equal to the hydrogen ion activity to the N power, to denote that stoichiometric coefficient, divided by the product, which is, or not the product, I should say, the reactant. So this is M N plus, and that's what we have. So we've got 3 different equilibrium expressions to describe those 3 different generic reactions. So complexation is going to be the development of a complex species between 2 or more previously independent components. So this is a process in which some central metal ion, which is going to accept electrons, and as such is considered what's known as a Lewis acid, and 1 or more ligands, which are going to be electron donors or Lewis bases, actually come together. So to illustrate this concept, we can think about what happens when we add ferric chloride to water. So we use ferric chloride in water treatment as a coagulant to help flocculate and remove suspended materials. And essentially, when we do this, we have ferric ions that are Fe3+, that react with water, and essentially we end up producing 3 different complexes, as what we've shown here. So we've got Fe with 1 water added, so we've got FeOH2+, we can add 2 waters, we get FeOH, and there's 2 of those groups attached to it, and then we actually have a third where we have 3 OH groups that are attacked. So there's a wide range of different complexes that form in this one solution. So in the example that I just showed, a ligand in that case was water, and it possesses electronegative atoms that have 1 or more pairs of electrons that can be shared. So just to illustrate, we can draw a water molecule where we've got our familiar H2O, and on there we're going to have 2 pairs of unshared electrons, and those can interact with our metal ion. Now other ligands that we could think about would be things like chlorine, ammonia, and so on. All things that have electrons that can be used for sharing. So for complexation reactions, we can develop equilibrium expressions as follows. So K, and we'll use a subscript stab 1 to define this as a stability constant. It's going to be equal to, again, the activity of our product. So in this case, it's Ml plus M minus 1. And then that's going to be divided by the activities of our reactants. So M plus times the activity of our ligand. So that expression provides us with the first stepwise stability coefficient for a complexation reaction. And we can make this more generic by talking about the cumulative stability coefficient, which is going to be beta. And essentially, beta is going to be equal to the activity of our product. So this is MLN plus M minus N divided by the activity of our metal ion, MM plus, times the activity of our ligand to the N power. So our next class of reactions are going to be redox reactions. And in this case, we think about the movement of electrons from one species to another. So oxidation is going to involve the loss of electrons from a species, while reduction is going to be the gain of electrons by another species. So if one species is oxidized, then another one must be reduced. So what we've got shown here is a redox reaction involving ferrous iron. So this is ferrous iron, and this is something that we oftentimes find in groundwater. And it's reacting with hypochlorous acid. So this is hypochlorous acid, which under many conditions is going to be what we call free chlorine that's added to drinking water as a disinfectant. So those two react, and the Fe2 gets oxidized to produce Fe3, and then the hypochlorous acid breaks apart. So this is an example of an oxidation-reduction reaction. So to describe redox reactions, we typically break them apart into half reactions. One of them is going to describe the oxidation, and the other describes reduction. Now, unfortunately, to confuse things, by convention, half reactions are written as reductions. So we're going to have the electrons all written on the left-hand side. Now, as we'll discuss later, the tendency for a reaction to occur is defined by its reduction potential. So we can find reduction potentials for reactions in tables in the scientific literature. So for this first one, E0, which is the reduction potential, and that's going to be in volts, it's going to be equal to 0.771 volts. And E0 for this other reaction, as it's written, and these are describing as the chemical reaction is written, is 1.224 volts. So what we can do is we can actually figure out what the net reduction potential is going to be. So that's E0 net. And in this case, it's going to be the reduction potential for our reduction minus the reduction potential for the oxidation reaction. So that's this one, and the overall reduction potential is going to be 0.453 volts. So for redox reactions, we can still develop an equilibrium expression, and for this one, we can say that K net is going to be equal to the activity of our products. So that's going to be Fe3 plus, since again the activity for water is by definition going to be equal to 1, divided by the activity for our reactants, so Fe2 plus, the hydrogen ion concentration, and in this case, because oxygen is a gas, we're going to define its activity based on its partial pressure. So that's the partial pressure of O2, and that's going to be to the 1/4 power. So we've talked about chemical reactions for a lot of inorganic species, but we can also think about other potential environmental fate processes. And of these, phase transfers are going to be important for the movement of materials into and out of waters. So we can talk about two kinds of phase transfers. There's going to be gas transfer and then there's going to be adsorption. So gas transfer is just going to involve the dissolution into or the volatilization of a chemical from water. So sometimes we want to add gases into water, so we might use a fine bubble aeration to get gases to be entrained in water. We do this to add oxygen during wastewater treatment. Sometimes we might want to have carbon dioxide added to water, like in a soda bottle. So we have CO2 in the gas phase that's going to be in equilibrium with CO2 in the liquid. And we'll see a lot more about that as we go through the rest of this course. Now, we can describe all of this in terms of what's going on at the gas-liquid interface, and that's just kind of what's illustrated here, where we have gas going from the gas phase and being dissolved into our liquid. So that was gas transfer, but adsorption is a similar process, and in this case, we have the removal of a substance from the water phase either onto or into a solid material, and then desorption is going to be the movement from the solid back into the water. So it's the opposite process. Now, the thing to point out, and why we're presenting this in this particular section, is that phase transfers are treated essentially to be the same as chemical reactions and are described using both equilibrium constants and reaction rates. So we can lump them all together when we talk about environmental processes. So we'll end the lecture today with a brief introduction to important environmental transformations of organic chemicals. So the first of these is going to be hydrolysis, which is going to be the reaction of organic compounds with water. And essentially, in these reactions, water is acting as a nucleophile, and this nucleophile attacks a covalent bond present in an organic chemical. And in some cases, these reactions are going to be acid or base catalyzed. But the point here is that we are taking water, and it is attacking a covalent bond, and effectively what happens is it breaks that bond apart, and you end up having a carboxylic acid that's produced, at least in this example, with the acid catalyzed amide hydrolysis of chloroacetamin's. Our second type of transformation of organic compounds is going to be photolysis, and at its simplest, this is going to be the interaction of light with an organic chemical. So light gets absorbed by an organic chemical. In this example, we have atrazine, and the chemical becomes excited, so it enters an excited state, and in this case it's just denoted with the star next to the atrazine, and then this excited state relaxes to a final product, and for this chemical it produces what's known as hydroxyatrazine. The structure for hydroxyatrazine versus atrazine is shown here. So photochemical transformations are very important for a lot of different chemicals. So our final organic chemical transformation are going to be redox reactions, and in this case, the organic compound gets reduced or oxidized by either inorganic or organic oxidants or reductants. And just what's shown here is the transformation of triclosan, which is added as an antimicrobial agent in soaps, into a series of products. And this occurs in the presence of hypochlorous acid, or free chlorine.